All right, Class 10, welcome to your final super quick revision for one of the most important chapters for your board exams, chemical reactions and equations. We're going to cover everything you need to know, so by the end of this, you'll feel totally ready to nail this section.
So tera dhyan kidhar hai? Your chemistry revision is right here. Forget all the stress, forget the confusion. We're about to make this chapter so simple and clear. Let's go get you those full marks.
Okay, here's the game plan. We'll start with the basics, then we'll absolutely nail balancing, fly through the 4 major types of reactions, and finish strong with redox. It's the perfect way to cover the whole chapter. Let's jump right in. First things first, let's build a solid foundation. You see, before we can even talk about all those cool chemical equations, we need to be crystal clear on the difference between a physical change and a chemical change, because that's where all the action happens. It's actually pretty simple. A physical change just changes the form, like ice melting into water. You didn't make anything new, and you can easily freeze it back into ice, right? It's reversible. But a chemical change, that creates a brand new substance. Think about burning paper. It turns into ash. You can't unburn it. That permanent, irreversible change is your big clue that a chemical reaction has happened. So a chemical reaction is just the process behind that chemical change. It's where the starting materials, we call them reactants, break their old chemical bonds. Then all the atoms get rearranged to form new bonds, creating completely new stuff. We call those products, and they have totally different properties from what you started with. So how do you actually spot a reaction in the lab? Well, you look for the telltale signs. Did the color suddenly change? Did the test tube get really hot or super cold? Did you see bubbles, meaning a gas was produced? Or did a solid suddenly appear in a clear liquid? These are your clues that, yep, a chemical reaction is definitely going down. All right, let's get into a skill that is, and I promise you this, guaranteed to be on your exam, balancing equations. Now, this isn't just about making things look tidy. It's about following one of the most fundamental laws in all of chemistry. And that law is the law of conservation of mass. It basically says you can't just create or destroy matter out of thin air during a reaction. What this means is the number of atoms of each element you start with on the reactant side has to be exactly the same as the number of atoms you end up with on the product side. That's the entire reason we balance equations, to prove this law is true. And the method is super easy. First, just make a list of all the elements in the reaction. Then, count up the atoms for each one on the left side of the arrow and do the same for the right side. Finally, you just add coefficients. Those are the big numbers you put in front, to make the counts on both sides equal. And remember, never change the little subscript numbers. Okay, let's do this one together. We have iron plus water gives us iron oxide plus hydrogen. Let's start with iron, Fe. We've got 1 on the left, but 3 on the right. Easy fix. We'll just put a big 3 in front of the Fe on the left. Okay, iron is balanced. Now let's look at oxygen. Oh, we have 1 on the left in H2O, but 4 on the right. So we'll put a 4 in front of the whole H2O molecule. But wait, by doing that, we've now got 4 times 2, which is 8 hydrogens on the left. On the right, we only have 2. No problem. We just need to put a 4 in front of the H2 on the right side. And now let's do a final check. 3 iron atoms on both sides? Check. 8 hydrogens on both sides? Check. 4 oxygens on both sides? Check. And boom, it is perfectly balanced. Awesome. Now let's get into the main types of reactions. We'll start with 2 that are basically polar opposites. First, we have combination, where 2 or more things combine to make one single thing. A plus B gives you AB. And then there's decomposition, where one big compound breaks down into smaller, simpler pieces. So AB breaks apart into A and B. You absolutely have to know these 2 examples. First, burning a magnesium ribbon. Remember the key observation here? It burns with a white, dazzling flame and leaves behind a white powder, which is magnesium oxide. Second, adding quicklime or calcium oxide to water. This thing reacts like crazy. It hisses and it lets off a ton of heat. The beaker gets really hot. That's a classic exothermic reaction. Now for decomposition, the breaking apart reaction. A compound won't just fall apart on its own. It needs a kick of energy. And depending on what kind of energy you use, we get 3 types. Thermal, which uses heat. Electrolytic, which uses electricity. And photolytic, which uses light. For thermal decomposition, the color changes are everything. Seriously, this is a huge exam question. Take ferrous sulfate. It starts as light green crystals. When you heat it gently, it loses water and turns white. Then, if you heat it really strongly, it breaks down into a reddish-brown solid, that's ferric oxide, and you'll smell a funky gas that smells like burning sulfur. So remember the sequence. Green to white to reddish brown. Burn that into your brain.
And here's the other big one, heating lead nitrate. It starts as a colorless, crystal-like salt. When you heat it, you get two dead giveaways. First, a yellow solid gets left behind. That's lead oxide. And second, you'll see these very obvious brown fumes coming off. Those brown fumes are nitrogen dioxide gas. Again, these observations are prime exam material.
Okay, next up, displacement reactions. The best way to think about these is like a competition. It's all about which element is more reactive, or you could say stronger. A more reactive element can literally kick out a less reactive element from its compound.
So how do we know who's stronger? We use the reactivity series. And here is an amazing trick to remember it. Just say this silly sentence with me. Katarina ne car मांगी Alto Zen Ferrari, फिर भी है क्यों मिली silver Audi. This lines up all the metals perfectly, from the most reactive potassium all the way down to the least reactive. This is an absolute lifesaver in the exam hall.
And here's the perfect example. Iron is more reactive than copper, right? It's higher up in our series. So, when you dip a plain old iron nail into a bright blue copper sulfate solution, the stronger iron kicks the copper out. You can actually see it happen. The solution's color fades from blue to a light green as iron sulfate forms, and all the displaced copper forms a brown coating right on the nail. So, if single displacement is one element kicking another out, then double displacement is more like a partner swap. You have two compounds, and they just exchange ions. The positive part of the first compound goes with the negative part of the second, and vice versa. And very, very often, this great swap results in a solid being formed out of two liquids. We call that a precipitate. And this is the classic example you need to know. You take two totally clear, colorless solutions, barium chloride and sodium sulfate, and you mix them. Instantly, a thick white solid appears out of nowhere. It looks like magic. This white stuff is your precipitate, barium sulfate. It's the textbook example of a double displacement reaction. All right, we've reached our final category, redox reactions. The name itself is a hint. It's a combination of reduction and oxidation. And here's the main thing to remember. These two things are like two sides of the same coin. You can never ever have one without the other. They always happen together. Okay, so this part is pure memorization. There's no way around it. Oxidation is the gain of oxygen, or the loss of hydrogen. And reduction is the exact opposite, the loss of oxygen or the gain of hydrogen. See how they're perfectly mirrored? One substance gains what the other one loses. Now, for the part that always seems to confuse people, the oxidizing and reducing agents. But don't worry, there is a super simple trick. First, just figure out which substance got oxidized and which one got reduced. Then, just swap the names. The substance that got oxidized is the reducing agent. Why? Because it caused the other guy to get reduced. And the substance that got reduced is the oxidizing agent. It's that simple. Just swap it and you'll never get it wrong again. And that's a wrap. We've covered combination, decomposition, single and double displacement, and redox. You've got the concepts, the key examples, and all the little tricks. You are now more than ready to